So continuing function series in calculus, this is graph of a function. Topics covered will be what does graph of a function mean, examples of graphs, definition of a graph of function, and some standard graphs, and a vertical line test in graphs. So first of all, what does graph tells us? Graphs have visually impact. By looking at the graph, we can tell much about the relationship between two variables, which is not clearly evident from just the equation y is equals to fx. So they reveal information that may not be evident from the algebraic descriptions given to us in terms of y is equals to f of x. So just by looking at the graph, we can tell much about the function. So for example, a graph is given to us in two variable. One is time here is in years, and another variable is production of some industrial product, and this is the graph. So we'll be discussing what it tells, what it describes. We are connecting the different years. This is just a rough sketch. So description from the graph we can tell is, first of all, it is the total production in an industry over a 5-year time span. The time is in years. It would be mentioned below whether it's in years or months. So this graph tells us the production of a particular industrial project or the product over a 5 years time span. Secondly, there is a peak in the graph which suggests the production is greatest at a particular corresponding time. Like here, it's around midway between 3rd and 4th year where the production was maximum. So this all we can judge just by looking at the graph. That's why graph is important. Now the second example, here the graph contains two variables. One is time and population on y-axis. There is some bound of the graph which is called upper bound, and this is the graph. So by looking at the graph, what actually we can tell, there is an increase in rate at first, and then there is a decrease in rate around upper bound. So this is called bounded population growth. The graph represents the growth of a population. These are the depiction we can study from the graph. Graph represents the growth of a population when with an upper bound, and secondly, there is a rate of increase of population growth, indicates rate of population growth which increases at first and then decreases with the size of population when it gets closer to the upper bound. See, upper bound here can be any environmental factor, or it can be a natural calamity due to which there is a sudden decrease in population rate has started. So this can be anything, but there is a bound for the population. That is why it is called bounded population growth graph. This all we cannot tell just by looking at y is equals to fx. Only graph tells us that much story. So next is definition. What is actually the graph of a function? What is the definition of this? The graph of a function f consists of points whose coordinates xy satisfy the value of the xy in equation y is equals to f of x for all x which are in the domain of f. So whenever x is a part of domain, we substitute the value of x and we get some value y from the equation y is equals to fx. Then we get a coordinate xy, and then plotting of that is called graph. How can we draw graph? This needs further understanding of few topics like derivatives, whether the function is increasing, decreasing, monotonicity of a function, maxima, minima, extreme values of a function. So these all are the concepts we need to draw a particular graph. But yes, of course, some standard graphs can be drawn. Standard graphs like which we generally use uh, very commonly, and they don't need much criteria. They won't even tell you about the details of the function, but we can have general criteria of how we draw, how they look like y is equals to x, or a few more. Here I am drawing some standard graphs. Y is equals to x. This is y is equals to x square, which has symmetry about the y-axis. Then there is y is equals to modulus of x, absolute value graph. This is also having symmetry about y-axis. Then y is equals to x cube. This have symmetry about origin. And then this is y is equals to root x square root function graph. Then we have asymptotic graphs of reciprocal functions. They are asymptotes. They don't touch. These lines don't touch. They are just parallel to the y-axis. Y is equals to 1 upon x. And then we have asymptotic graphs in first and second quadrant. This is a standard graph of y is equals to 1 upon x square. And if we have the asymptotic graph in just first quadrant, then it is a reciprocal square root function. Y is equals to 1 upon square root of x. But these are just standard graphs. We can just have the knowledge. And then we have the vertical line test. What it tells, the vertical line test. The curve lie in the plane is the graph of a function. Not every curve is a graph of a function. See, graph we can plot, but whether it will be function or not, that tells vertical line test. Vertical line test, a curve will be a graph of a function if it intersects no vertical line for more than once. The graph can, if the graph is cutting all the vertical lines, whatever the vertical lines you draw, and it cuts not more than once, then this is a graph of a function, otherwise not. Why so? Because by definition of fx, definition of a function, for one value of x we can have one and only one value of y, right? Whenever we are substituting any value from the domain, there should be a unique value in the range. That's the criteria which tells us geometrically, whenever there is a vertical line with equation x is equals to a, that cannot cut graph at more than one's place. That is the vertical line test. So by looking at the graph, we can tell whether it is the graph of a function or it's a graph of not a function. For example, suppose this is the graph. these two graphs which I have drawn at first, you draw any vertical line in the graph, it cannot touch any vertical line more than once. It's not touching any vertical line more than once. So these are the graphs of a function, because no vertical line intersects the graph more than once. In last two examples, these are the examples of not functions, because vertical line it intersects the graph at more than one place. This is the graph of not a function. This is also not function, because we are getting more than one value of y for just one specific value of x. So they are not functions. The graph intersects, at least one vertical line is present there which is intersecting curve at more than one places.